Imagine an AI that can learn any task from playing video games to control robots without engineering tricking its codes for every new challenge. This isn't science fiction. It's the promise of Dreamer V3, a revolution AI involved in 2023. Good sir. Today, our group will present a breakthrough in AI mastering deserved domain through world model with Dreamer V3. Imagine an algorithm that learns any task from playing arcade to control robots without manual turning. This is not longer theoretical. Dreamer V3 introduced this in this landmark in 2023's papers make it real. Other than that, this paper also reveals how Dreamer V3 cracks this problem using world models, a simulated imagination that predict outcome before taking action. So now we'll look about our content will be discussed. First is the mastering 150 tasks about robotics, gaming, logistics with one set of fixed setting. Next is the achieving the impossible, for example, collecting diamond in Minecraft from scratch. Next, scale seamlessly from tiny to a massive AI model. So by the end, you will see why this isn't just a progress, it's a leap toward general intelligence after our discussion. Now I'll pass my mic to my teammate.
Okay, thank you, Raisin. My name is Leong Ting, and now I'll talk about the background. To begin, reinforcement learning split into model-free method like DQN or OOP that learn policy by trial and error by need massive data, and model-based method that first learn a dynamic model to plan or generate synthetic experience. Predict every pixel is expensive and noise. Since most visual detail is irrelevant to fix this, lantern space worst model encode observation into compact lanterns. Predict how those lanterns evolve under action and decode pixels or reverse only an auxiliary signal, making training far more stable and sample efficiency. Next. In 2018, Bennett introduced a recurrent state place model, RSSM, that learns lanterns dynamic and uses lantern space MPC to solve continuous control tasks with far fewer interaction than model-free method. Then in 2020, Dreamer V2 built on this by imagining lanterns rollout, rolling out the RSSM for many steps, and training an actor critic network on this Dreamer trajectory. Dreamer V2 achieves state-of-the-art efficiency on humanoids and vocal, but still need per task tuning and only tracked continuous domain. Last, at the same time, Mu0 learns a lantern's model predicting policy logic, value, and reverse, skipping fixed pixel construction and use motor tree search to master redirect games like Atari. Yes, it's direct action. Finite horizon planning doesn't work for continuous control or long horizon space river tasks. So Dreamer V3 closed this gap by learning a recurrent state phase model from pixels, training entirely on imaging, rule out and apply fixed robustness trick, normalization, reverse scaling, balance loss. So the same agent excels across direct, continuous, and spare rewards domain without any per task tuning. Thank you, and now I'll pass my mic to Daniel.
Okay, thank you, Tingy. So right now I will talk about, my name is Daniel. So right now I will talk about motivations. Motivation is a central challenge in artificial intelligence is building agents that can learn and perform well across a wide variety of tasks and domains without requiring manual tuning or domain-specific expertise. While reinforcement learning, or we can say RL, has shown remarkable success in areas like games and robotics. Current methods are often brittle. They rely heavily on carefully designed architectures, task-specific hyperparameters, or events expert data to function effectively. Adapting these algorithms to new tasks typically demands significant human interventions, computational resources, and trial and error experimentations. Okay, so we can go next. All right. This bottlenecks limits the scalability and general applicability of RL to real-world problems. The goal is to move toward a general-purpose learning algorithm that works out of the box across visual, spatial, continuous, discrete, and procedurally generated environments. The Dreamer V3 algorithm is motivated by these visions. It uses word models, which are internal simulation of the environment, to learn effectively and robustly across more than 150 different tasks with a single configurations, thereby overcoming the drawback of current methods. It is noteworthy because it is the first algorithm to gather diamonds in Minecraft from the start, a task that is considered a big challenge in the artificial intelligence because of its intricacy, lack of rewards, and lengthy planning horizons. Dreamer V3 is a big step in making reinforcement learning more robust, general, and useful, which will pave the way for wider real-world usage. Thank you. So right now I will pass my mic to my friends.
Thank you, Daniel. Now I'm going to talk about the challenge of learning and leveraging robust work models and balancing multi-objective losses and generalization. In a training work model involves losses whose gradient magnitudes can diverge by millions. If reconstruction dominates, the latent space collapses. If reward prediction dominates, the visual detail vanishes. Dreamer V3 normalized these scales through KL balancing with free bits and a small representation penalty, equalizing contributions from every term. Crucially, it uses one fixed set of hyperparameters and replay ratios. No per task tuning or human play traces, so a single configuration reliably trains on over 150 tasks. This out-of-the-box loss weighting matches or exceed the performance of specialized, hand-tuned baseline in every domain. In this slide, a robust work model must both auto-encode past frames and predict future states, and reward without sacrificing one for another. It must resist latent space collapse by aligning gradients from the heterogeneous losses so that the representations remain stable even as input shift. Finally, it must conquer sparse reward, hard exploration tasks like the Minecraft diamond mining, where thousands of random stats yields no reward. By combining Simlog, Simex, input transforms, two hot regression targets, and intrinsic exploration bonuses, Dreamer's V3 recurrent state and space model with discrete latent weaves these techniques together, empowering a single agent to learn accurate, generalizable work model and plan effectively across richly varied environment. Thank you. And now I pass it to my teammate.
Okay, thank you, Jiaming. Hi everyone, I'm Wu Zhenyu. I'll now walk you through the methodology of Dreamer version 3, how it tackles the challenges we just heard about. Dreamer version 3 is a model-based reinforcement learning algorithm with three key components, a word model, a critic, and an actor. Next slide. First, the word model encodes sensory inputs into latent variables and predicts future states, rewards, and terminations. It uses a recurrent state space model, combining an encoder, a sequence model, and a decoder. The training objective balances a prediction loss, a dynamic loss, and a representation loss. To stabilize learning across domains, Dreamer version 3 applies KL balancing, free bits, and the Simlog transformation, which compress the large value targets symmetrically. This allows the latent space to remain informative and consistent, even under sparse rewards or high-dimensional inputs. The critical learns to predict a distribution over future returns from imagined trajectories. It uses lambda returns and a two-hot encoding scheme for robust multimodal value estimation. The critic is trained both on real and imagined rollouts and is regularized with an EMA of its own parameters. Finally, the actor selects actions to maximize expected return using a reinforced loss for entropy regularization to ensure generalization across tasks with vastly different reward scales. Dreamer version 3 normalizes returns using percentiles rather than row advantage or standard deviation. Together, these components form a unified and stable learning pipeline. Dreamer version 3 can imagine futures, evaluate them, and act accordingly, all with fixed hyperparameters, no expert demonstration, and no handcraft turning. This design enables it to solve over 150 diverse tasks, including Minecraft's diamond mining challenge, entirely from scratch. Thank you. Then I'll pass to my friend.
My name is Leonard Tazian, and I'll be explaining the imagination in Dreamer V3. So my group has introduced the Dreamer V3's core components. So for my part, I wanted to highlight what I believe is the most significant aspect, the profound power of its world model and its capacity for imagination. This represents a fundamental shift. Unlike the traditional reinforcement learning that learns directly from countless real-world observations, Dreamer V3 first builds a highly accurate internal stimulation, a compact latent world model directly from raw pixel data. So once this world model is learned, the agent can then imagine or dream up the future scenarios entirely within its internal model. It stimulates interactions, predicts outcomes, and plans actions without needing costly real-world engagement. This ability to dream and plan within its own stimulated reality is what truly sets Dreamer V3 apart and underpins its remarkable capabilities. This imagination capability offers critical advantages that underscore Dreamer's V3's significant contribution to the DRL. So firstly, unparalleled sample efficiency. By learning from imagined experiences, Dreamer V3 achieves high performance with dramatically fewer real-world interactions, a game changer for costly applications like robotics. And secondly, the vital for mastering diverse domains is exceptional generalization. Because the agent understands underlying dynamics, its world model adapts seamlessly to a vast array of tasks and environments with fixed settings. This out-of-the-box performance is a major step forward. Finally, imagination is transformative for sparse reward problems, famously seen in collecting diamonds in the Minecraft. Dreamer V3 can explore and plan long horizon strategies within its imagined world, effectively practicing to reach distant goals without real-world trial and error. So in my opinion, this emphasis on robust world models and imagination is a fundamental leap, bringing us closer to truly general-purpose AI agents capable of adaptable real-world learning. That is all for me. Thank you very much.
Thank you, and I will introduce the datasets. Unlike traditional R approaches that rely on expert demonstrations or curated datasets, Dreamer V3 doesn't use any pre-collected data. It learns entirely through agent-environment interaction, meaning the data is generated as the agent explores and improves. This shifts the focus. Instead of designing datasets, the author designed the environments. Each environment becomes a dynamic data stream. Next, please. The paper uses 8 benchmark domains, treating them as live data generations. Together, they offer a wide variety of tasks and observation types, from pixel images to proprioceptive vectors, as well as both discrete and continuous control challenges. Each domain has a fixed interaction budget, which essentially defines how much experience the agent is allowed to collect. So rather than feeding in static data, the model learns by continuously rolling out its own experience in diverse settings. Next, please. Here we show what one of those environments actually looks like as a dataset. Minecraft gives the agent a low-res image, inventory counts, health bars, and bars +1 rewards for reaching key milestones, like crafting a tool or finding a diamond. Episodes are capped at 30 minutes. This is the closest the paper comes to a data section, and even here, the data is entirely generated on the fly. I will pass my mic to next member.
Okay, thank you. So next for the experimental outcome. In this study, Dreamer V3 has evaluated across 8 diverse domains covering over 150 tasks to test its generality and robustness using fixed hyperparameter. This is significant as most reinforcement learning algorithms require task-specific learning. Dreamer was compared to expert Q methods and a standardized PPO baseline. A major highlight was its application to Minecraft, a complex and sparse reward environment, and also all models were trained on a single NVIDIA A100 GPU. Next. Okay, here is an overview of the benchmark result across different domains. Dreamer outperforms state-of-the-art algorithms in almost every benchmark, including both classic control problems and high-dimensional fission tasks. For instance, in Atari, Dreamer beat Mujero, which is already a very powerful model, but with much less computational cost. It also beat PPG and Rainbow in ProGAN, Impala and R2D2 Plus in DMLab, and DRQ V2 and Curl in Fission-based control tasks. This consistency suggests that Dreamer design, particularly its world model-based planning, make it more sample efficient and generalizable than many prior methods. Next, a standard result was Dreamer's success in Minecraft, where it collected diamonds from scratch, something no prior method had done without human data or curriculum tuning. Unlike VPT, Dreamer used only its default hyperparameter and still solved this long-standing challenge. This demonstrates its effectiveness in open-ended, real-world-like settings with sparse reward and large state space. Then, to understand what driver Dreamer performance ablation study were run on 14 tasks, removing key components like KL regularization or return normalization caused noticeable drops in performance, especially the KL objective. Notably, Dreamer relies more on unsupervised signal like filter state prediction than on task-specific rewards, making it well-suited for pre-training on unlimited data in future application. Finally, Dreamer was tested at model size from 12 million to 400 million parameters across tasks like Crafted and DMLab. It showed stable, scalable performance. Larger model achieved better results with less data. Replay ratio adjustment also improved data efficiency. This finding confirmed Dreamer's scalability and its potential for real-world deployment when more computational resources are available. The next part, I will pass it to my friend.
Thank you to my teammates. Now I'll do the conclusions. In summary, Dreamer v3 proves that one algorithm can conclude countless domain by replacing manual turning with robust world models and innovations like small log predictions. It achieved the impossible, like finding diamond in Minecraft vast, unpredictable worlds. This isn't it just about the game? It's a blueprint of a real AI. Next, let us see about the efficiency, which is learn faster as the model scale, the adaptability, same code of robots, logistics or science, and the accessibility for the open source for everyone. So the paper closing words say it's best one algorithm, diverse domains. As we refine this approach, we move more closer to the AI that understand our world, not just using it. So this is the discussion of our paper. Thank you for you guys for listening. Let us build the future together. Thank you.